This is lecture 2. First, we'll do a quick recap of what we saw in the earlier class. So we started with sampling. And what we do in sampling, we take a continuous time signal x of t and convert it to a discrete time sequence x of n, right? And we saw how to model the sampling operation, and it can be done as follows. So we take the continuous time signal x of t, say it has a profile versus time like this, something like this. This x of t. So we took the signal x of t and multiplied with a periodic train of impulses, which I denoted it as p delta of t. And how does this impulse train look like? We will have impulses at 0, ts, 2 times ts, and so on. And strength of all these impulses is 1, right? And the product signal, we denoted it as x delta of t. And how does this look like? So we'll again have, let's say this is the envelope, the continuous time signal. So we'll have the same impulses at 0, ts, 2 ts. Just that the strength of these impulses will depend on the value of the signal x of t. So here it will be x of 0. Here the strength of this impulse will be x of ts. This will be x of 2 ts, and so on. Right? And finally, we'll have a block here that converts these continuous time impulses to discrete time impulses. So now this will become n. So this is x of n, that is the discrete time sequence. So we'll have discrete time impulses like this. Okay. And in the frequency domain, the spectra looks like this. So let's say x of t has a spectrum x of f that is band limited from minus b to plus b. Well, we saw that the frequency response, that is a frequency domain representation of the impulse train, that is the Fourier transform of the impulse train, will again be an impulse train, and the impulses will be located at multiples of fs. Right? In the time domain, we see that we are multiplying x of t with p delta of t. Right? So in the frequency domain, the spectrum will convolve. So what will happen after convolution? Around each of these frequencies, we have these impulses, right? So because of that, this spectrum will get shifted to each of these frequencies. We'll have one copy around 0. So this is p, this is minus p. Let me make some space. So we'll have a replica around fs. So this frequency is fs minus p. And then we'll have a replica around minus fs and other multiples of fs as well. Now, if you look at the discrete time Fourier transform of the sequence x of n, the frequency, discrete time frequency is omega, and even the discrete time spectrum will have a similar shape, right? Only the frequency axis will get scaled, right? So 0 will remain as 0, fs will become 2 pi, minus fs will become minus 2 pi, and so on. And in general, we saw how a continuous time frequency f gets mapped to a discrete time frequency omega. And this was given by this relation. Omega is 2 pi times f by fs, right? Because fs we saw gets mapped to 2 pi. So which means the frequency f should get mapped to 2 pi times f by fs. Simple logic. Right? Now here, please remember that this portion that I've highlighted here is merely a mathematical model for representing the sampling operation. Right? This is not how we will implement sampling in practice. Okay, so we'll not generate this kind of impulses and multiply this with the continuous time signal. Okay, so this is simply a mathematical model for representing sampling. And we are doing this, and we have constructed this model for analyzing the operation and see how the signal gets transformed. Okay. We also saw very briefly how to convert this discrete time sequence x of n back to the continuous time signal x of t. Right? And how do we do that? Say this is x of n. So it has these discrete time impulses, say from 0, 1, 2, and so on. So first, we convert these discrete time impulses to continuous time impulses like this. And they'll be located at 0, ts, 2, ts, and so on. So now if you look at the frequency domain representation, so here we'll have the spectral replicas around multiples of 2 pi like this in the discrete time frequency. The moment we convert these discrete impulses to continuous time impulses, the spectrum will again look similar, just that the replicas will now be at multiples of fs like this, right? And from this, how do we get back the continuous time signal x of t? Well, we recognize that x of t has a spectrum that is only this portion, right? So what we did, we added a low pass filter here that extracted only this portion of the spectrum, right? We didn't get into the details of what is the specification of this low pass filter, its cutoff frequency, and so on. We will do that in this lecture, but this was the overall picture. Okay. And in sampling, we saw one more important thing. What was that? Well, we saw that if we kept reducing the sampling frequency beyond a point, this replica will start overlapping with this portion, right? And in order to prevent that, what we needed to do, we needed to ensure this frequency fs minus b was greater than this frequency b. So this gave the condition that fs must be greater than 2b, which is the Nyquist criteria. Right? And we saw that if we do not satisfy the Nyquist condition, what we'll have aliasing. And we'll not be able to reconstruct this continuous time signal x of t from x of n. Right? And we also saw that a frequency fs plus delta f, when you sample it at fs, looks like a signal at a frequency delta f, right? So similarly, fs minus delta f will also look like minus delta f, right? I mean, for real signals, there is no differentiation between plus and minus frequency, so this is simply delta f, right? Well, this is because, like, let's say if you take cos, let's say cos 2 pi times minus delta ft, well, we know this is same as plus cos 2 pi delta ft, right? Because cos of minus x is cos of x. Now, if we have it in sine, we'll have sine of minus x is minus sine of x. So this will simply be minus sine of this, right? So we'll have the same frequency. Right? So with this information, so let's look at the frequency axis once again. So let us say this is minus fs by 2, 0. This is fs by 2. Fs by 2. Okay. Let me expand the axis further. Okay. Now let's consider a frequency that is this, and let's call it this. Let this frequency be fs by 2 plus some delta f. Okay. So how can I represent this frequency? I can represent it like this, right? So fs minus fs by 2 minus delta f, correct? So well, if you compare it with this, what we see, if we sample this at fs, we will get fs minus 2, fs by 2 minus delta f, right? So fs plus any frequency, when you sample at fs, you'll get back that frequency, right? So similarly, here you have fs minus this frequency. So when you sample it at fs, it will look like the same frequency. Okay. So what we'll have after sampling, it will look like a frequency here, right? So fs by 2 minus delta f, right? So in a way, you can think of fs by 2 as some point. So it's like a folding axis, right? So beyond which any frequencies will get aliased back, right? So this frequency, you can think of it as it is folding back to this point, right? So this is fs by 2 minus delta f. This is fs by 2 plus delta f. And because of this reason, this Fs by 2 is also called the folding frequency, right? And this process of aliasing is also referred to as folding, okay? So we synonymously say a frequency, folds back or aliases back. Okay, some terminology now. So let me draw the axis once again. So 0, this is Fs by 2. So let's say this is Fs. So this range of frequencies from 0 to Fs by 2 is called the first Nyquist zone or first Nyquist band, right? So this is the range of frequencies, which can be sampled properly at a frequency of Fs, right? Beyond that frequency, if you sample it at Fs, we will incur aliasing, okay? So the next range of frequencies from Fs by 2 to Fs, this zone is called the second Nyquist zone, right? And so on. Okay. Well, in the last class, we also saw that, let's say we have a signal which is band limited, minus B to plus B. When we sample it at Fs, we notice that we will not only be processing the signal, but we'll also be processing this kind of a broadband noise, right? And we know that any signal that is Fs plus or minus delta F will alias back to delta F, right? So what will happen when we sample the signal at Fs? So this range of frequencies around Fs, that is Fs minus B to Fs plus B, right? So this range of frequencies will fold back. Noise from this range of frequencies, right? Similarly, around minus Fs, similar range of frequencies will fold back. And this doesn't stop there. From any multiple of Fs, this band of frequencies, that is this range of frequencies, will fold back. Okay, and we saw that this can be very severe and it can even drown the signal. And what was the solution to this? Well, we decided that we'll put a low pass filter, which was called the anti-aliasing filter. Okay. So before sampling at Fs. And what does this anti-aliasing filter should do? This should make sure that the noise that is getting folding back, that is noise that is getting folded back from high frequencies, is attenuated to the required value. Okay, and this is where we had some problem. So let's see what that is again. Right. So this is the frequency axis. So let's say this is minus B and plus B. Here is my signal. Okay. And we saw that this is the broadband noise. Right. Well, the frequencies from which the noise can alias back is this, right? Fs minus B to Fs plus B. This is the first band of frequencies from which noise can alias back, right? And we'll have other multiples of Fs as well. So even from 2Fs within this band, that is 2Fs minus B, 2Fs plus B, we'll have noise folding back. Okay, right? So the minimum frequency from which noise can alias back is Fs minus B, right? So this is the band of frequencies. Okay. Well, if we decided to sample the signal at the Nyquist rate, that is Fs is 2 times B. So what will happen to the same figure we saw earlier? So this will be at minus Fs by 2. This will be at Fs by 2. Right? Why? Because P is Fs by 2. Okay. And the minimum frequency from which noise can alias back, what is this? This is Fs minus Fs by 2. Is simply Fs by 2. Right? So what this simply means is that any frequency just above Fs by 2 will start folding back, right? And the band, that is Fs minus B to Fs plus B, what does that become now? So that is Fs by 2 to 1.5 times Fs. That is 3 by 2 times Fs. So this is Fs. This is 3 by 2 Fs. So this is the first band of frequencies from which noise can alias back, right? So what the low pass filter must do, it should allow all the frequencies within the signal bandwidth and must attenuate all the frequency components from which noise can alias back by a fixed amount, right? And we saw that because of this, our filter characteristics must have a sharp transition, right? And this was essentially a brick wall filter kind of characteristics, right? And we also saw that this is not possible to realize in practice. So what's the solution? Well, let us say this is my signal bandwidth B. Okay. Well, let us say that a practical filter, a realizable filter in practice has some frequency response like this, right? It has a very slow transition. Okay. And let us say this is the tolerable level of attenuation for us, right? So the frequency from which the noise can alias back must be at least attenuated by this level, let us say. Okay. So what we need to ensure that? We need to ensure that the minimum frequency from which noise can alias back is at least attenuated by this much, right? Because all the other higher frequencies will be attenuated even further. So what we do? We choose this point as Fs minus B, because Fs minus B is indeed the minimum frequency from which noise can alias back, right? So what does this give? Fs minus B is here and B is here, right? So Fs minus B is clearly greater than B, which means Fs is greater than 2 times B, right? 2B was the frequency that is dictated by the Nyquist condition, right? So Nyquist condition says that the minimum sampling frequency must be 2B, right? So I call this as the Nyquist frequency, say Fn. So what we are essentially doing now is we are sampling it. We are sampling the signal at a frequency that is much higher than the Nyquist frequency, right? And this act of sampling the signal at a frequency higher than the Nyquist frequency is called oversampling. Okay. And the ratio of the sampling frequency Fs to the Nyquist frequency, that is twice the signal bandwidth, is called the oversampling ratio, which is also abbreviated as OSR, right? And I might also use the letter M, the symbol M, to represent OSR in some lectures. Okay. It turns out that this oversampling has some more advantages, and we will return back to this concept later. Okay. So now we saw that to solve the problem of anti-alias filter, that is to ease the anti-alias filter design, oversampling is a solution, right? It's a possible solution, right? So with Nyquist state sampling, we saw that we required a sharp transition like this in the filter characteristics. And with oversampling, we can afford a very smooth roll-off, which is easily realizable in practice, right? And I also mentioned that oversampling has more advantages, right? So what's the catch here? There is nothing like free lunch, right? Someone has to pay for your lunch, right? So there is nothing that is there is no idea, no concept that has only advantages, right? There should be some disadvantage or some, catch to it. And what is it in this case? Well, here, please note that the actual sampling frequency at which we could have sampled the signal is 2 times B, right? That is the Nyquist frequency. But instead, we are sampling it at much higher frequency, right? And what does it translate to? Well, we need to operate the circuits at much higher frequency, right? So which means we need to charge some capacitors and discharge them much quickly. And what does it relate to? If the capacitance value is same, we need to pump in more current, which will in turn result in higher power consumption, right? So that's a disadvantage or drawback to this. But this is usually not a problem, because if you don't do oversampling, you may not even be able to realize this kind of an anti-alias filter, right? So usually we always see that ADCs are always oversampled, you almost will never encounter an ADC where you exactly sample it at the Nyquist state. And this oversampling factor OSR can be anywhere between 2 to 4 for some ADCs. And for some other class of ADCs, it can be much higher. It can be even of the order of few hundreds as well. Okay. Well, so far we have been looking at signals that were centered around 0, right? That had spectral content around 0 or baseband signals. Okay. So now let us consider a signal which has its spectral content centered around a carrier frequency, say Fc. So since it's a real signal, I'll have it also around -Fc. Okay. And where do we encounter such signals? Well, this is an RF signal, right? So what do we do? If you want to transmit any signal, so we take the signal, modulate it, and then upconvert it to a frequency Fc, right? Well, let's see, this point is Fc plus B, that is this, and this is Fc minus B. Okay. So let us say you want to digitize or sample the signal without incurring aliasing. Well, what does Nyquist condition say? We need to sample it at twice the bandwidth of the signal, right? So in this case, you will think that this is the complete bandwidth, right? So it is taking this entire space from 0 to Fc plus B. So if you sample it at twice Fc plus B, you will indeed incur no aliasing and you can digitize the signal without any issues. Okay. But actually, if you think about it, well, we are not completely interested from 0 to Fc plus B, right? Well, this part is the actual signal, that is actual, like information that is of interest to us, right? So in an RF receiver, what do? We usually down convert it we do something called mixing operation, and we down convert this signal back to DC, and then we sample it and digitize it. Well, of course, sampling will have some kind of an anti-alias filtering. So before sampling, we do this anti-alias filtering and then sample it. Okay. So the question is, let me draw this down. Okay. So this is the spectrum. Well, now the question is it possible to combine sort of these three? Not the filtering part, that is mixing operation, that is this down conversion operation and sampling. Well, the answer turns out to be yes. So the reason is because of the following. Okay. So when you sample a signal at Fs, so what happens? The spectrum of that signal is sort of repeated, or you can say it is getting shifted to multiples of the sampling frequency, right? That is k times Fs, where k is an integer, right? So let's say we have this RF signal here. So centered around Fc, I have this. Around -Fc, I have this. Okay, this is 0. Let us say I sample this at Fc. Okay. So what happens? I'll have first spectrum will be repeated at kFs, right? So let's say for k equal to 0, what do we have? We'll have the same spectrum, right? So -Fc and plus Fc. Now for k equal to 1, what will happen? This entire spectrum will shift to the right by an amount Fc, right? So this -Fc, what will get? It will get shifted to the right and we'll get a component of the same spectrum here. Right? So let me draw it properly. Similarly, this Fc will get, like shifted to 2Fc. Okay. Now for k equal to -1, what will happen? This portion will again shift to the left by Fc. So we'll have a component at -Fc. And this will again come to 0. So we'll have, like the same thing repeated. Right? So we can do this for other multiples of Fc, and you'll finally notice that when you sample it at Fc, you'll have the spectral copies at all integer multiples of Fc. Okay. So well, if now we have sampled it, so now in the discrete time, what will happen? So the frequency axis will get scaled. This will be 2 pi minus 2 pi. And we got back the signal, right? So we sort of down converted the signal from Fc, right, to the DC, that is baseband. just by sampling it. Okay, and this sort of sampling operation also can help us to down convert signals. So this is also sometimes called as sampling mixers, and the minor variant of it is also called as passive mixer. Okay. Well, of course, what we have to do, well, we not only will be sampling the signal, we'll also be sampling the broadband noise, right? So what we do, we'll have to ensure that we are filtering and making sure that the frequencies from which the noise can alias back is attenuated by a reasonable value. Okay, and here what are the range of frequencies from which noise can alias back? Well, from around every multiples of fc it will alias, right? So starting from k equal to 0, right? So which means from minus b to plus b, this noise will alias. So second, it will be from 2 fc. So this band of frequencies will alias back and so on, right? So what we have to do, so this will be what? 2 fc minus b, right? So this will be 2 fc plus b. So we need to have a filter. I didn't draw it properly, but it'll look something like this, right? That makes sure that the frequencies from which noise can alias back is attenuated to a reasonable value. Okay. And so essentially what we'll have this anti-alias filter, which I call AAF. So this is essentially now a bandpass filter, right? And then you sample it as. And this scheme is also known as direct RF digitization, right? Because you are directly digitizing the RF signal, right? By directly down converting it as well. Okay. Now let's take it one step higher. So we saw that if we have this RF signal here, something like this, minus FC and FC. Okay. We saw we could sample it at FC and then do down conversion, right? So we sampled it at FC, and we saw that because of sampling, spectrum shifts to multiples of FC, right? And that is k times FC. And we saw that for k equal to 1, this portion comes to baseband, that is 0. And for k equal to minus 1, this portion comes and down conversion happens. Okay. So well, now let us say you sample it at FC by 2. So what will happen? The spectrum shifts to multiples of FC by 2. So we'll have these shifts happening around k FC by 2, right? Well, now for k equal to 2, what will happen? We'll have the same thing, right? The spectrum will shift by a factor by an amount FC. So let's draw the complete spectrum. This is F. This is FC minus FC. For k equal to 0, what will happen? You'll have the same thing. For k equal to 1, the shift will be by an amount FC. So let us say shifting to the right by FC. So this will be what? Minus FC by 2. For k equal to minus 1, this will shift to the left by an amount FC by 2. So this will be FC by 2. For k equal to 2, the shift will be by an amount of FC, right? So you'll have something like this, right? Well, so this also seems to solve the problem, right? So what is the catch here? Again, as I mentioned, there is nothing that comes for free, right? We'll have to pay some price somewhere. Well, again, if you look at the noise problem, so we have this broadband noise, right? Remember that earlier when we were sampling it at FC, let's go back to this slide. So minimum frequency from which noise can alias back is this, right? So B, and on the other side, the frequency minimum, the minimum frequency from which noise can alias back is this point, right? 2FC minus B. Right? So the bandpass filter, so if this is 0, what it had to do, this is B, and this is, let's say, 2FC minus B. So these are the 2 points, 2 frequency points at which bandpass filter must provide the minimum attenuation required, right? Well, now what we are doing, we are sampling at FC by 2. So, which means from where all the noise can alias back. So let me draw it here separately. This is FC, this is 0, let's say this is FC by 2. Okay. So which means now the noise can alias back from multiples of FC by 2, right? So which means if this is FC by 2 plus B, this is FC by 2 minus B, this band of frequencies will also alias back, right? So what we have to do, what the bandpass filter has to do, this is the required bandwidth. It has to pass these frequencies properly, that is till this point. And the attenuation must start from this point, right? So similarly on the other side, this is 3FC by 2. You will have 3FC by 2 minus B, right? So attenuation must start from this point itself. So earlier what you could do, you could have, if let's say this is B, the bandpass filter could have done something like this. But now you see the bandpass needs to, provide sharp filtering. Okay. So which means as you keep reducing this, frequency, it can from FC by 2, let's say you go to FC by 4. This down conversion will still happen, but what's the problem? We'll start increasing the complexity in the bandpass filter design, right? Because the bandpass filter, the characteristics of the bandpass filter needed will become sharper and sharper. And that will impose additional design constraints. Okay. This is also known as subsampling. Right? And why is it called so? Well, because if you look at this frequency, what is this? This is FC plus B, right? So if you were to follow Nyquist's condition, you would have sampled the signal at twice this frequency, that is twice FC plus B. But instead we are sampling it at FC or even fractions of FC, right? Let's say FC by 2, FC by 4 and so on. So in short, we saw different kinds of sampling, right? First, we saw the Nyquist sampling, where we sample the signal following the Nyquist condition. And we saw that if we do that, the anti-alias filter required will be an ideal brick wall filter, which we cannot realize in practice. So what we do is that we usually oversample the signal in practice. Okay. And on the other end, we also saw we can do subsampling. And this can be done for down converting an RF signal from a carrier signal FC to a baseband. Okay, now that we have spent some time to study various aspects of sampling, let's spend some time to understand the inverse process, that is reconstruction. So here, what is the goal? We have to convert the discrete time sequence X of n to the continuous time signal X of t. And how do we do? Well, let's say this is our discrete time signal. See, this is 0, 1, 2. So first we saw we'll convert it to continuous time impulses. So this is 0, TS, 2 TS, and so on. So if you look at the spectrum, it will look like this. So we'll have replicas around multiples of 2 pi in the discrete time frequency. And the moment we convert it to a continuous time impulse, this is minus B and plus B, the replicas will be centered around multiples of Fs. So this frequency is Fs minus B. This is minus Fs. Okay. And let's say we are sampling the signal. We had sampled the signal X of t at Nyquist state. That is, we chose Fs to be twice B. That's the maximum signal bandwidth here. So we chose twice B. Okay. And let's say these are the samples that we obtained. By sampling X of t at Nyquist state, we obtained this sequence X of n. So how will the spectrum actually look like in that case? Well, here we know B is Fs by 2. So which means this is Fs by 2. And Fs minus B is also Fs by 2, right? So essentially, we'll have something like this. right? This is 0, this will be Fs by 2, this will be Fs. Similarly, you'll have the same here. So this will be 2 pi, this will be pi, this is b minus 2 pi, and so on, right? And then we recognize that this is the actual signal spectrum that is of interest to us. So we'll put a low pass filter here. And how should the low pass filter look like? Well, it should allow all this portion. This is the signal, right? And it should completely filter the rest of the spectrum, right? So this portion should be filtered out. This is the low pass filter, right? And we can clearly see that we again end up with a brick wall filter. Okay. And some terminology now. So these portions of the spectrum where we have these replicas, they are also called as images, right? Because they are image of the main signal spectrum, right? So now let us say we had used this ideal brick wall filter here. How will the time domain signal look like? So we would have exactly got the continuous time signal x of t like this, right? So let's say this is 0, this point is ts, this is 2ts. So we can see at the input of the filter here, we already knew these time instant values, right? The signal value at these time instants. So what this filter is doing is that it is filling the in-between values, okay? And we know that for an ideal brick wall filter, the impulse response, h of t, for this will be a sink, right? So which means it will look like this. And it only goes to 0 as t tends to infinity. So essentially, we have an infinite impulse response, right? The impulse response exists for infinite amount of time. And we know if the input to the filter here, it says x delta of t and the output is x of t, the relation between them is given by the convolution integral, which is this h of tau x delta of t minus tau d tau. Right? And since we know that this impulse response h of t exists for infinite amount of time, right? So essentially what the filter is doing, it is using the input value at say infinite seconds earlier than the current input, current time instant t, and uses all the past input samples, right? The value we need is x of t. What it is doing, it is taking all the previous values of the input x delta of t minus tau, and based on all the past input values, it is filling these in-between samples. Sorry, filling the in-between values. Okay. And as we saw earlier, we cannot realize the brick wall filter in practice, right? So what do? Well, we usually oversample, and the moment we oversample, these images are spaced apart, right? So this is 0, this is x. So if we do that, then we can have a realizable low pass filter and kind of filter it. Of course, we cannot completely filter off the images. We can filter them to a reasonable extent. Okay, again, this portion is just a mathematical representation, and this is not exactly how we will realize this reconstruction and reconstruction process in practice, right? Because we obviously cannot generate these continuous time impulses, right? So let's see how it is generally done in practice. So ideally, according to the model, this is what we wanted, right? So we wanted these discrete time impulses to be converted to continuous time impulses at 0, ts to ts, right? But obviously, we cannot generate impulses. So what we do in practice is the following. We take these samples and generate a signal like this. Okay. So let's say this is t, this is 0, ts, 2ts, and so on. Well, we know the value of the signal at these time instants, right? At 0, ts, and 2ts that are given by this sequence x of n. So what we do is we construct a signal like this. So we hold the value at the first sampling time instant t equal to 0 and hold it for the entire sampling duration. And when the next sampling instant comes, we switch to the next value and again hold it and so on. And this process is called zero order hold, also abbreviated as ZOH. Okay. Well, this is called zero order hold because if you look at it, To fill the in-between samples, in-between values, what we do, we are just holding the existing value, right? Whatever value we had at the sampling instant. We are not using any past values of the input to reconstruct, right? This is unlike the ideal case where this brick wall filter, that is the sinc impulse response filter, was using the input samples from the previous time instance to reconstruct the current input sample, to reconstruct the current output sample. So essentially, this one had an infinite memory, right? So we can think of it as an infinite order. But here we are not using any memory. We are only using the current input sample and holding it throughout. So essentially it has zero memory. So we call it zero order. So well, this is what we do in practice, right? This is what we do in practice. So let us see how we can model it, right? So in our equivalent model, what we did, we had just converted these discrete time impulses to continuous time impulses. And to model this, what we can do is we can consider that these impulses are being sent to a filter with an impulse response P of t, where P of t is like this. So it is a pulse from 0 to Ts. So it is equal to 1 from 0 to Ts and 0 elsewhere. So let's convince ourselves that this operation indeed generates this signal. Okay. So again, let's say this input is x delta of t. I call this as x hat of t, let us say. How is x hat of t related to x delta of t? X hat of t is x delta of t convolved with p of t. And what is x delta of t? That is this signal. That is essentially a train of impulses, right? So it is delta of t minus nts summation n equal to minus infinity to plus infinity. But the strengths of these impulses are determined by the input signal, right? So this strength is x of 0. The strength of this impulse is x of ts and so on. So what I'll have here, I'll have x of nts as the scaling factor. And this is getting convolved with p of t, right? And if we know that if we convolve a signal with an impulse, we'll get back the same signal. So what will end up is this, x of nts, p of t minus nts, right? So let's say for n equal to 0, what we have x of 0 times p of t, and that is what this is, right? And for n equal to 1, we have x of 1, that is this value, times p of t minus ts, right? N equal to 1 here. So what we have, the pulse is getting shifted by ts, and we have this. And then we go ahead, right? So essentially, this operation can be modeled like this. Okay. So if you think about it, ideally what we wanted a brick wall characteristics in the frequency response, or a sinc in time domain, right? Sinc impulse response. But if in this process, what we are essentially doing, we are having a filter with a brick wall or a pulse kind of response in time domain. And of course, this translates to a sinc in the frequency domain, right? And how will the frequency response of this look like? Well, we know it's a sinc. So if I plot the magnitude, it will look like this. So this is mod p of f, right? And what are the zero crossing values? Well, a small digression. So how can we find the zero crossing values easily? Well, we know that Fourier transform is what? We are essentially multiplying a signal with sinusoids of different frequencies, right? So here, p of t is getting multiplied with sinusoids of different frequencies and we integrated. That is what p of f, right? So p of f is integral p of t e power minus j 2 pi f t dt. And p of t is what? This is a pulse. So it is 1 only from 0 to ts. So if you multiply a sinusoid with this pulse, we will have only the sinusoid existing for a period of ts, right? From 0 to ts. And if the Fourier transform is 0 at these points, what it means? The integral is 0. So essentially, integral of a sinusoid from 0 to ts, it is 0. And what sinusoids can they be? What sinusoids can satisfy this condition? Only sinusoids that have one complete period in ts, right? So the first frequency is fs, and the second is 2fs, right? Even if I have two periods within one ts, this will be 0. So this is 2fs and so on. Okay. But ideally, what we wanted a brick wall characteristics like this. But instead, when we are doing the zero order hold, what we are having a sync kind of a frequency response. Obviously, this might not be good enough for filtering the dark images or filtering the images, that is these portions. So in practice, what we do is after this, we also have a low pass filter for additional filtering. Okay. So let's see some example. Here I'm showing a continuous time signal in blue. So it is some kind of a Gaussian pulse. And what I'm doing, I'm sampling it. I'm actually oversampling it, let us say. And the red points, lines are the discrete time. Is the discrete time signal, and these are the discrete time samples. Now my goal here is to reconstruct this continuous time signal from these samples. Well, what do I do first? As I mentioned, I do zero order hold first. So I take these sample values and hold it for one sampling period completely. And I keep repeating it. So this is the zero order hold, right? And this obviously is not matching the continuous time signal. Only if you look at it with your artistic eyes, you can see this kind of follows the input signal, right? And why is that? Because the sync frequency response that the zero order hold does is not good enough for filtering the images. So what is done here is that we are taking the sequence and doing a zero order hold and getting the signal here, and that is this signal in pink. Now to make this better, what I do in the next step, after zero order hold, I give it to a low pass filter. Okay, additional low pass filter. And the moment I filter, the output is the black curve, and we see that the curve is more smoothened, right? It looks kind of starts to look more like this blue curve. In the next step, what I'm doing, the same filter here, I've made it a better low pass filter so that it filters the images much better. And once I do that, I get the final black curve here, and we can clearly see that it more or less matches the input, the continuous time signal, right? Obviously, there is some delay because filters are all causal, and the output will come after some delay, right? So we can stop at this point, and we can continue from the next class.